Let's discuss another really important skill related to concentration that we'll use in lab all the time, and that's dilution. In fact, you probably do this already in your life all of the time. When I make like juice for my kids, I make sure I take like the concentrated juice stuff and I add the water, and I'm doing a dilution right there where the juice is the concentrate is my solute and the water is my solvent. All right. So let's say in chemistry terms what that really is. So dilution is just going to be the addition of additional solvent to change the concentration of our solution. And that's going to decrease our concentration of that solute in the total solution as we add more solvent. We're just changing that ratio because that's all concentration is. It's just here's a ratio of how much solute I have to how much solution. And if I add more solvent, I increase that volume of solution without actually changing the solute amount. And so that means that I'm going to have a lower concentration overall. I like this picture that's on the screen because the number of dots are supposed to represent solute particles. And you can see that there's the exact same number of them in both of these beakers. The only difference is the amount of water that's been added to the beaker relative to those particles. And so what happens is that we have something constant between this before and after solution, and that's the number of moles of our solute particles. So if the moles in both of these are the same, so I can say the moles initially are equal to the moles in the final solution, then I can build up a relationship around that equality. Because if I have, and I'm gonna take my molarity, and I'm going to call it C for now. So textbooks will sometimes show M for molarity, C for concentration in this equation. But if molarity equals moles over volume, and we're going to call molarity concentration in this case, we can rearrange this equation so that way moles is equal to volume times concentration or molarity. And so if we're saying that the number of moles initially is equal to the number of moles in the final solution for our solute, that hasn't changed, and that N is equal to volume times concentration, then our initial volume times concentration is really equal to our final volume times our final concentration. And we usually use 1 and 2. So the typical way you'll see this is C1 V1 equals C2 V2. Another way you might see this is as M1 V1 equals M2 V2, where M is concentration and molarity. In our C1 V1, the concentration is molarity as well, except it's C, so it's both. And I'll probably flip between these all the time just because I've seen them both ways so often. So let's do an example of how this works. So how much water must be added to a 50 milliliter 5 molar solution of sodium hydroxide to form a 0.25 molar solution? In these problems, the equation is pretty simple to solve. The trick is just making sure you are appropriately identifying which is concentration 1 and which is concentration 2. So I'm going to write out all the information that's given to us. We have 50 milliliters of a 5 molar solution. These are linked together in how the problem is worded. They're saying you have a 50 milliliter 5 molar solution. So these are one thing. And we want to figure out how to get to a 0.25 molar solution. What we don't know is the volume of that 0.25 molar solution. And so here's our second one. So we're starting with something more concentrated and we're going to something less concentrated. So our 50 milliliters of 5 molar is our first like our before or number 1, and our 0.25 molar is our number 2 situation or our final solution. And we really need to know that volume. And look, I have 3 variables that I know and 1 I don't. It's perfect. So I'm going to plug these in. So C1 V1 is going to be my concentration is molarity. Sorry. So I've got 5 molar. And I've got a volume of 50 milliliters. That's equal to some new volume, volume 2, times 0.25 molar. And I'm going to solve this, but I'm going to first talk about units for a second. Remember, we talked about molarity as big M, but it's also moles per liter. So I'm going to go through and change that big M to highlight something. Right now, my units don't match at all. So I have volume in liters for my molarity, and I have volume as milliliters in my volume of my solution. And normally this wouldn't work at all. I would need to convert this 50 milliliters into liters. And you can do that. You can always convert it into liters. This would be 0.05 liters and use that instead. But because this equality has the units the same on both sides of the equation, I can keep it in milliliters, but it will report a value that then is in milliliters too. So if I solve this as is, I'll get an answer in milliliters. If I convert my 50 milliliters to liters and then solve it, I'll get an answer in liters. So you can choose whichever one you prefer. So volume 2 is going to be equal to 5 moles per liter times my 50 milliliters divided by my 0.25 moles per liter. And just to kind of prove this, look, our moles per liter cancel out, and I'm left with units of milliliters for my answer. So it actually works out. So calculating this in my calculator, I end up with a value that is 1,000 milliliters. So what does that mean? That is volume 2. That is the total volume of the solution after I dilute it. And so now, is that what the question is asked? So we're asking how much water needs to be added to a 50 milliliter solution. So I need a total volume of 1,000 milliliters, but I'm starting with 50 milliliters of 5 molar. So my answer is what's added. I'm going to highlight that here. So that's going to be 1,000 milliliters. That's my total volume minus the volume I already have, 50 milliliters. So again, that's my total volume minus my initial volume. And so I'm going to add 950 milliliters to my solution, my 50 milliliter 5 molar solution, and then I'll have a concentration of 0.25 molar.